everyone to this week's HPL seminar. Today we'll be hearing from Tao Liu. Tao is currently a researcher at the University of Alberta, designing implants for talus replacement surgery. Tao completed his bachelor's and master's in mechanical engineering from Northeastern University in China. Following, he pursued a PhD at the University of Alberta in biomechanics, focusing on using finite element analyses to estimate load sharing on the lumbosacral spine during standing and bending. Tao completed his PhD in 2018 and then spent 2 years at Halifa University examining the effect of obesity on low back pain. Tao's research interests include spine biomechanics, implant design, and applications of machine learning in large-scale biomechanics datasets. Tao is proud to have received 4 patents on robotics and implant designs. Tao hopes to one day find a faculty position to continue working in the biomechanics field. In his spare time, he enjoys hiking, traveling, and trying new cooking recipes. As a reminder, I'll first turn it over to Tao for his presentation, and then we'll have a question and answer period to follow. So you're welcome to start sharing your screen, Tao, and thanks in advance.
Thank you very much for the introduction. Can you see my screen now?
Looks great.
Okay, thank you very much. So good afternoon, everyone. My name is Tao Liu. So I'm here today to talk about the design of universal talus implants for total talus replacement. So to provide some background, so avascular necrosis is the death of the bone tissue due to a lack of blood supply. So this can happen to most joints, and one of the joints is talus bone. So when it happens, there are 2 treatment plans. So the first treatment plan is to use talus fusion, which fuses the talus bone with adjacent bones. This can lead to a lot of pain and decrease the joint mobility. An alternative treatment is to use customized implant. So it can maintain joint mobility, but it involves a longer and more expensive design process. However, there are clinically identified needs for more accessible and more affordable talus implants. So the goal of this project is to design a series of universal talus implants that can account for talus shape variations. So as our design can account for talus shape variations, so it means that it can be prefabricated, therefore decreasing the cost of the talus implants and making it more accessible for patients. So in order to achieve the goal, what I did first was to find the representative implant sizes and shapes using statistical shape modeling of talus bones. So this can give us a better understanding of principal shape variations of talus bones. So next, we examined the implant fits using finite element models by comparing the contact characteristics of our design with that of the biological models. So this can provide information on similarities of the contact pattern, contact area, and the contact stress between our design and biological models. So after the second objective, we found that the metal-based talus implant can cause local stress concentration. So in order to improve our design, we came up with a new design, which is to add a layer of compliant material on top of a metal-based talus implant. So we investigated the effectiveness of a compliant material at reducing implant bone contact stress And after the third objective, we found satisfactory results between our design and the biological model. And then we decided to further test our implant using dynamic models by evaluating the implant effectively steering gait using musculoskeletal models. Now let's take a look at them one by one. So for the first objective, to find the representative implant sizes and shapes, we used statistical shape modeling of a talus bone. First, we developed an algorithm to register different talus bones based on a data set of LAMP8 tilai. And the advantage of doing this is that it can avoid observer bias. And so the registration is achieved using an optimization. So after registration, so all different bones can be represented by a fixed number of points, and then we can perform a principal component analysis based on this after registration. So after the development of the algorithm, the first thing I did was to test the accuracy of the algorithm. So I checked the circumference between registered bone, which is highlighted in blue, and the accurate bone, which is highlighted in the red, in 3 perpendicular planes. So in X plane, we can find that the circumference error is around 0.56 after registration. And in Y plane, it's around 0.56 millimeter after registration. And in Z plane, the circumference error is relatively larger, which is 1.84 millimeter. So after performing principal component analysis, we can find a mean shape for both male and female tilai. And here I also listed the first 5 principal shape variations for male and female. So we can see that for the first principal shape variations for both male and female, it is focused on the talus size. And for the remaining 4 principal shape variations, it focused on the local variations. So here is a visualization of the deviation between the mean shape and the first 5 principal shape principal component eigenvectors scaled by 3 sigma. So we concluded that we found that the first 2 principal shape variations can account for around 60% of the talus shape variations. And here, so using the male average talus shape as a reference, I compared 3 different implant designs. So the first comparison is with a universal talus implant designed by Travado in 2017. And so in Travado's study, she used the talus bone that has the least deviation from the remaining bones in a data set of LAMP8 tilai. And the second comparison was with a universal talus implant that has been modified by a surgeon with 20 years of experience. And so his design is based on the Travado's design. And the last comparison was with the average female talus shape we found in our study. So we found that there was around 8% of points that has a deviation greater than 1 millimeter for the first 2 comparisons. And for the last comparison, so there was a percentage of 0.6 points that have a greater deviation, greater than 1 millimeter. So through the first study, we concluded that the average male and female TALUS implant shapes are geometrically similar when scaled to the same volume. And we also found that the first two principal components that can be taken into consideration to improve geometrical accuracy in the TALUS implant design. So next, we examined the implant fit using finite element models by comparing the contact characteristics from our design and the biological methods, the biological TALUS bones. So here, we evaluated 3 TALUS implants. So the biological bone is the reference, and the first implant we used is called a customized implant. So customized implant is basically reconstructed from the CT scans of the patient. And the second implant is called universal TALUS implant, so which is designed by Travado, which is a TALUS bone from patient that has the least deviation from the remaining patients in a data set of 98. And the last TALUS implant is SSM, is what I found using statistical shape modeling. And in order to account for the loss of cartilage volume, I also considered 2 ways to account for the loss of cartilage. So the first way is called scale, and the second method is called offsite. So for offsite implant, so we offsite the surface of the TALUS implant by 0.5 millimeter along the normal direction of the TALUS bone. And for scaled implant, we use a scale factor to increase the volume of the implant. So here we can see from the deviation contour. So when we use the offsite method, so there is a uniform deviation of 0.5 millimeter. However, when we use the scaled method, we can't guarantee that the deviation is 0.5 millimeter everywhere. So the advantage of using scale method is that it can maintain the surface curvature. So we investigated 3 critical postures: dorsiflexion, neutral standing, and plantar flexion. And for each implant, we have 3 models. The original one, and we used 2 methods to account for the cartilage loss. So for each implant model, we have 3 models. And we using the biological model as a reference. So in total, for each subject, we have 30 finite element models. And we investigated 4 patients. So for our finite element model, it's composed of 5 pieces of bones. So a tibia bone, fibular, and TALUS bone, and a calcaneus bone, and the navicular bone. So the far end of the adjacent bones are constrained as rigid body, and the center of the TALUS bone is also constrained as the rigid body. So the entire analysis is composed of 3 consecutive steps. So in the first step, so we fixed the TALUS bone, and we moved the adjacent bones towards the TALUS bone to form an initial contact between the TALUS bone and the adjacent bones. So there are 4 pairs of surface-to-surface contact was established in this model. And in the next step, so we are going to fix the displacement of the adjacent bones and unconstrain the TALUS bone to let it find its best position to simulate the surgery procedure. So for the last step, so we applied a load of 2000 Newton at the top of the tibia to simulate the critical situation for ankle joint. So here is the results for the first subject. in dorsiflexion. So we can see that for biological models, we have larger contact areas and smaller maximum contact pressure. This is reasonable. And when we compared the results from the customized implant with the biological model, we can find that the contact pattern is very similar because essentially they have a similar shape. And when it comes to the universal and SSM implant models, so the contact pattern changes a little bit. And another finding is that for all implant models, we observed high maximum contact pressure and decreased contact area. So the similar conclusion can be found for neutral standing and plant flexion. So through the second objective, we found that the biological models had the largest contact areas and smallest peak contact pressures. And whereas implant models had smaller contact areas and larger peak contact pressure. So this, for the second conclusion, we got is customized scale had a larger total contact area than SSM scale and universal scale. However, the variations are very limited. So after the second objective, we found that metal-based TELUS implant can cause local stress concentration. So we came up with a new design, which is to add a layer of a compliant material, which is polycarbonate urethane, to reduce the contact pressure between our implant and the adjacent bones. So we investigated. We used 4 subjects, and for each subject, we used 1 biological TELUS bone and three different TELUS bones, with and without PCU coated. So in total, for each subject, we have 7 finite element models, and we analyzed the 4 subjects. So in total, we have 28 finite element models. And here is the results for the first subject. So when it comes to the biological model, we found the same conclusion as the second study. We found that the biological model can predict a larger contact area and a smaller maximum contact pressure. So when it comes to the PCU coated customized SSM and universal TELUS implants, we found a comparable contact characteristics with that of the biological model. However, when it comes to the metal-based TELUS implant, which is referred to as the COCR here, we found 4 customized SSM and universal COCR. They all predicted high maximum contact pressure and reduced contact area. So here is our conclusion. So first, PCU coated implants have a comparable contact area and contact pressure to the biological models. And stiffer material implants without the PCU coating have a higher contact pressure and smaller contact areas. And adding a layer of a contact compliant material like PCU can reduce the contact pressure and increase the contact area. So through the objective 2 and objective 3, we found a good design that can predict comparable contact characteristics with that of the biological models. So next, we we want to further test our implant design by using dynamic models. So we decided to evaluate the implant effectiveness during the gait using musculoskeletal modeling. However, the existing musculoskeletal models are generally simplified the ankle joint as a rigid joint, so it cannot predict contact characteristics. So the first thing we did is to develop a musculoskeletal model that can predict contact characteristics in the ankle joint. So here we implemented contact characteristics between the fibula and the talus and the tibia and the talus joint using elastic foundation formation. So here is our ligament architecture. So we included 19 different ligaments in our model. And here is a model validation. So we compared the passive stiffness of our developed ankle joint with Chen's work in anterior posterior direction. So here we used the same loading conditions. So we applied a moment of 8 Newton meter. So here we can see that the video shows that the contact between the talus and the tibia. So sorry, here we can see that there is a contact between the talus and the tibia and the fibula here. Instead of unlike other musculoskeletal models, they used a rigid joint. And for the second model validation, I compared my results with the existing experimental study under the same loading scenario, which is under a compressive load of 600 Newton. So the experimental results for ankle number 1 and ankle number 2 is from the work of Andrews in 2017. And the last result is the result from my model. So we can see that under the loading scenario, our model predicted a maximum contact pressure of 2.5 megapascal. And this is very similar to the maximum contact pressure measured for ankle number 2. And in terms of contact area, so our model predicted a contact area of 645 millimeters square. And this is comparable to that of ankle 2, which is 493 millimeter square. So after validation, I performed a gait analysis using lower body, and the kinematic and ground reaction force data was obtained from the literature. So after simulation, we can also check the contact characteristics in the ankle joint. So here I extracted the contact characteristics during gait for 1 gait cycle. So, and with an interval of 20%. So we can see here at the 60% of the gait cycle. So our model predicted the maximum contact pressure, which is around 9.5 megapascal. And at 0% of gate cycle, we can see that the contact is in the posterior region of the talus. And as the gate is progressing, so we can see that the contact pattern is moving from the posterior to the anterior direction. So the first chart here shows the variation of the contact force during one gate cycle. And the second chart shows the variation of the contact areas during one gate cycle. So we concluded that the current study developed a novel musculoskeletal ankle joint model with contact mechanics implemented in tibio-talar and fibio-talar contact. So the designed PCU-coated talus implant got patented in 2021, and part of the initial results has been in use in the University of Alberta with positive clinical results. So, and for the future directions, we are planning to test different talus implants using developed musculoskeletal models, and we are planning to perform more clinical trials with our design. Thank you.
Thank you, Tao.
No problem.
Great. So with that, I'd kindly ask the audience members that if you're comfortable to please turn on your Zoom camera to allow for a better discussion. To ask your question, you can use the raise hand feature or type your question in the chat box. Amin, please start us off.
Hello, Tao. Nice to see you again. Thanks for the presentation.
Thank you.
Okay. I didn't understand how this mean shape model is going to be used in the clinic. In the traditional in the traditional method, we use like CT scan to segment the talus bone, and then out of that we create a geometry, and then we can design and manufacture an implant for the talus, right? Now you have this mean shape model, and you have two variations of it. You can scale it and you can offset it. So let's say a patient comes to the clinic, the patient requires talus implant. How do you want to use this mean shape to design the implant for the patient?
Thank you for this good question. So when we found the mean shape, so we will use the male average as the design, and then we will scale it we will design 10 different sizes of talus implants. So this 10 different sizes will account for the shape variations that we found using our data set of 98 patients. So so when our patients have a fractured talus, so we will follow the same procedure. We will take a CT scan and find the volume of the original talus implant, and then we will use that as a reference to find the category, which is the sizes that the patient need. So we will scale our talus. We will give the corresponding talus implant for that patient. That's our strategy.
Okay, so you have like 10 categories, which has
10 different sizes, basically, yeah.
Talus bone, and then you just based on the volume of the patient's talus bone, you decide which category, which sizes would work for the patient, right?
Yeah. So basically, these 10 sizes can account for the shape variations, which is the principal shape variations we found and scaled by positive and negative 3 sigma. Yeah.
Okay, thank you.
Brent, please go ahead.
Yeah, thanks for that. I really enjoyed that talk. I like all that work. It's really great. So, you know, oftentimes when you do that kind of the MSK modeling, we'll sort of limit the degrees of freedom at a specific joint like rather than trying to model the ligamentous structures and other things like that. So like at the knee, we might limit it to, you know, the sagittal plane motion and not try to deal with the other degrees of freedom and the constraints imposed by the meniscus and the ligaments and stuff. And I hope I didn't miss it and tune out for 2 seconds, but I didn't know what exactly you were doing with the degrees of freedom at the talus joint and whether or not you had to model the ligamentous structures there too. Can you just talk a little bit about some of the constraints that you have to impose in the OpenSim model when you do that elastic foundation analysis?
Sounds good. Thank you very much. So, so for the OpenSim model, because our objective is to find the to evaluate the effectiveness of a different talus implant during the gait. So, however, the existing models usually simplify the ankle joint as a rigid point, so which has 3 degrees of freedom, as you said, and this doesn't meet our requirements. So we found a method. So basically, this method has been implemented in the knee joint by a researcher in Switzerland. And then we found that we can do the same thing for the ankle joint. So for the ankle joint, so we have 3 degrees of freedom, but this time we didn't use 1 point as a joint. So we created 2 contact pairs. So we have 1 contact pair between the tibia and the talus, and another contact pair between the fibula and the talus. And then we use this contact and we allow the penetration between these 2 surfaces so that this penetration can be used can be created as a function between the contact pressure. So, and then we use this to replace the original rigid joint. So the constraint of this model is that the relative motion between the fibula and the talus is not considered. This is the major limitation. This is because when we have too many degrees of freedom, the musculoskeletal model is not stable. So we can only focus on the major motions, which is the contact between the tibia and talus joint. Yeah,
I think I get it. So once contact is established, it's a tied, it's a tied constraint. Yeah. And okay. All right. Yeah. Thanks. All right. Nice.
I have a question, Tao. You showed a lot of results that were trying to look at how your implant contact pressures compared to biological.
Mm-hmm.
Once we have one of the bones being in contact being an implant, is comparing to the biological bone-on-bone contact pressure what we want to do, or could the one remaining bone potentially sustain a different contact pressure?
So, when we compare the contact pressure, we focus on the different. We are making sure that we are comparing the same cartilage. So, for example, we have 4 types of cartilage in the ankle. So there is a cartilage between the tibia and the talus, and there is a cartilage between the fibula and the talus. So when we compare, we always compare the same type of cartilage. That's why when I show the results for each phalanx animal, model, there are 4 types of the cartilage. So we use the biological model because we want to take it as a reference so that we can know how far we are from the biological one. If this high contact pressure can cause pain for patients, or if this high contact pressure is reasonable, or if this contact pressure exceeds the physical limits.
Okay, that makes sense. Thanks. Walter, go ahead.
Yeah, thank you. Thank you for a very clear talk. I have a series of questions, and maybe I start out with a couple of technical questions before I go into a couple of clinical questions. The first thing that really surprised me was when you did, an accuracy of your shape of the talus. You did that by measuring the circumference and comparing the actual circumference to the circumference of your model. And that seemed, to me at least, a bit of a strange way, but because, you can have very similar circumferences, but very, very different shapes. So how do you justify that?
Thank you for your question. I think it's a very good question. So when we compare the circumference, so we use instead of using one plane, so we use the 3 perpendicular planes. So this is trying to avoid the weird shapes, like you said, for maybe the circumference in one plane is small. However, the entire shape is varies a lot. So yeah, we compared this way because this is easier to. This is the easiest way to check, and it's this is the easiest way to check. And in addition to this, we also compared the 3D deviation between registered bone and the accurate bone, but I didn't put those results here. So using geometric software, in 3D for 3D shapes.
Yeah. The other question that I had is that, it makes a lot of sense to me when you just have the metal implant and you contact that with some other bone, that you get a smaller contact area and higher peak pressures compared to when you put your compliant PCU material on top of it. But I was wondering, adding that PCU, did that add any clinical constraints, like how durable is that, for example? Did the clinicians have any concerns with doing that?
That's again, that's a very good question. So when we consider this new design, so the first challenge we need to solve is the adhesion of between the medical grade material and the metal-based design. So first thing we did is we did some mechanical test. So we put some lattice or some special structures on the top of the metal implant, and then we coated the material. Basically, we melt the medical grade material and inject it on the entire metal-based talus implant. So the feasibility is under testing now. So we have designed some samples, and so we are still under testing for this new design. And from the perspective of practical, so I think it's feasible because in our team we have a surgeon with 20 years of experience, and so if the design is okay, so I think he's able to put it in the patient.
Yeah. Kind of a follow-up question to this, I was wondering, because very often in joints, we are not only concerned about the pressure type of forces, but we are also concerned about the shear forces. And I was wondering what the metal surface kind of a coefficient of friction was and what it is when you add the PCU. For example, did you change friction in a substantial way that might potentially negatively affect the cartilage on the other bones that surround the talus?
We considered this factor when we purchased our PCU material, and in our model we also changed a little bit, but not very much. So when we purchase those PCU materials, they always provide us a sheet of parameters they have tested. So we used we considered the surface toughness of the design. So we considered the surface fraction of our design by using different different types of mold. And this is still under test, so I don't have any more further information for this. But we considered this as a factor.
Great, thank you.
Thank you very much.
Amin, go ahead.
Did you use Thales implant designed by Min Shape method for any patient? Or it's just like in the research stage?
So we have produced one, and so for universal Thales implants, we have 6 clinical trials, and for the SSM, so I think there is one patient we are trying to put it in, but I didn't I can't see it for sure, so I haven't talked to our surgeon for a while. So yeah.
Yeah,
But it's in our plan. It's on our list. Yeah.
yeah, that would be nice to do like a longitudinal study and get patients' feedback about how comfortable it would be that implant and how is the range of motion, pain level. Yeah, to see the performance of the new implant. Thank you.
Yeah, I totally agree with you on this point.
Walter, go ahead.
Yeah, I have a couple more questions if nobody else wants to jump in here. Very similar to what Amin was asking, because at the very end you said, you have some pilot results and you said clinical results, and you said there were positive clinical results. Can you just elaborate in a sentence or two, how you identified that this was a positive clinical result and what that means to you?
Oh, so when I said positive results, I refers to the 6 clinical trials that we have done with I think with customized implant and universal implant, and with one more patient for SSM implant.
The other thing that I was wondering is, the talus naturally has some ligaments that reach over to other bones, and that keeps it kind of place. So when you implant, when you put in that implant, that talus implant, how do you stabilize it? Is it just stabilized by the surrounding bones, or do you try to mimic some ligamentous attachment like it had before?
So are you talking about models or talking about the surgeon?
No, I actually talk about the surgery, yeah, because I know what you did in the model, but I'm really more curious about if they try to somehow attach this artificial talus to some ligaments and hold it in place like it naturally would be, or if it's purely kept in place by the bones surrounding it.
So for our clinical trials, we didn't. So when we take out the patient's the fractured talus, we need to cut those ligaments attached to it. And when we put a new one, so this new one, we can just open the cut of the patient and put that implant in the patient's joint, and it will automatically sit there. So that's the best position. So we didn't adjust anything because it can't be maintained when patients work with the implant. So we didn't adjust anything. We just put it there, and it will automatically adjust.
Okay. And the last question that I was curious about is, you told us a lot about when you do the finite element modeling and the contact stress calculations. You told us a lot about the actual implant and the properties of the implant and the properties of the PCU. But how did you get at the model parameters for the remaining bones that surround the talus? How did you get a cartilage thickness and cartilage properties and those type of things?
So most of the data are from literature. And I think this is the least concern we need to worry, is that because we always use the biological talus as a reference. So we followed the same procedure, the same material, and the same loading scenario. And we always compared our implant results with respect to the biological model instead of the absolute value from the experimental study.
Thank you.
Reza, go ahead.
Thank you, Tal, for the great presentation. I had just some questions. First one was, you applied 2,000 Newton force for
Yeah.
all the samples. I was just curious to know that if this force varies between patients and models.
So we use the same force for all patients, which is 2,000 Newton, because in literature, so we found some, we wanted to use a force, we want to simulate the extreme dangerous situation. So that's why we used this large force. It's the same for all patients.
Same form. Okay. And then you just apply, you just put the cartilage on the bone. Is the cartilage thickness variation like considered in the model, or how do you add the cartilage to the model?
So for the cartilage, so we just we guaranteed that the cartilage of the cyclist on all the talus on all the bones remain the same. However, the areas of the cartilage is based on the potential contact area. So we didn't control the total contact or total cartilage area on the bones. So we just make sure that the cartilage area is big enough for contact.
Okay, thank you. Nice.
No problem.
I have another question, Tao. I think in your first objective, you showed that the male and female shapes were geometrically similar when scaled. And I feel like the implant community often is criticized for only having implants based off male scans or male models, but are your findings showing that actually if talus implants were only modeled and scaled off male participants, that would be a reasonable estimate?
So I think it's the main conclusion we got is that the talus shape is not significantly affected by the gender, and because based on the first principal shift variation, we found that the difference between different talus is the sizes. So we then we decided to use the average shape as the design, and then scaled it up and down to account for the shape variations. However, there will be some variations due to other principal shape variations. However, based on our finite element test and deviation contour, it's within 1 millimeter. So, and we found that 1 millimeter is usually a threshold used in the literature for the talus fracture. So we use that as a reference, and think the other principal shape variations is not as important as the first one. And the other advantage of doing this is that if we only use if we only consider the size as a factor, so we can design 10 sizes of talus implants. However, if we add another principal component analysis, so we need to design more talus implants. This is not convenient for prefabrication and for the patients to use it.
Yeah, that makes sense. Great, Don, please go ahead.
Hi, Tao. Thanks for the presentation. And it's not often I get to thank somebody for citing my work. Thank you. I'm just curious. I feel like I have to say something. Are you familiar with any load-bearing implants that are used today that involve this polycarbonate urethane on a metal backing like that?
So I read something in the literature. There was a design about the knee. So, but it's just like it's one disc which is made out of PCU. It's completely different from our design. That's the only design that I know of based on the PCU material. I don't know any.
Just feels like you have a really tough road to travel there in terms of getting the marketplace to accept that soft coating on a metal implant, because it's just so hard to believe that it wouldn't delaminate or break down or something else. But my follow-up question is, a lot of times when implants are designed, one of the considerations is, what do you do if there's failure? What's the revision option? And I guess the nice thing about a fusion is you still have bone there, where once you take the talus out, what's I guess the revision solution is to put in a second talar implant, pull the first one out and put a second one in or something. Have you thought about that?
That's a very good question. Yeah. So we consider that factor, but I didn't actually thought of that question as deep as you do. So when we design our implants, so the wear of the talus implant is also a factor. So when we always need, we usually perform some mechanical test to test the wearness of those materials that we used. But as you said, if a patient has a total talus replacement, and if they need any revision, maybe a possible solution is to use a laser talus implant. But I think this is something that I need to consider further in the future. Yeah.
Yeah, I would just encourage you to think through the lens of applications where you have no alternative. So if somebody has a cancerous lesion or something where you'd have to take out the entire talus, you don't have a choice of doing fusion. And maybe it's somebody who has metastatic disease and has a finite length of their life left. It seems like in that situation, having some kind of application that would buy you a couple of years would be really big. But I'm trying to imagine the 30-year-old who has a fracture of the talus and has kind of avascular necrosis, and you're talking about putting an implant that you hope might last 60 years, and it's just hard to imagine. It's a really tough challenge there. So my hat's off to you to kind of tackling it, but I think it's going to be a tough road to travel. I'll just say that. Yeah,
that's true. So when we design our talus implants, it's always used for those patients that has the talus bone of those patients are dead. And another situation I can think of is that if the initial fusion surgery is loosened and they can't use it anymore, maybe we can just take the fractured one out and use our designed talus implant. But as you said, I think this is a question we need to consider further in our future design. Yeah. Thank you very much for your question.
Other questions from the audience? Okay, with that, please join me in thanking Tao for his presentation, and thank you to all the audience members for their questions. Next week, we'll be hearing from Emily Bishop, and her presentation will be on
we might never know.
Suspense.
we might.
offloading, a biomechanical evaluation of spring-loaded knee brace. Sorry, did I freeze?
You froze for a second there, but everybody was in suspense. Was actually a really good freeze at the right moment, just when you were announcing what's happening next week.
It was like American Idol.